feedback or any questions at any point, please feel free to stop me. And yeah, I can get started. So today I'm going to be talking about building reliable computer vision systems. Oh, I forgot that this needs some setup. Great. So I'm going to be talking about building reliable computer vision systems. So the visual world has an infinite amount of visual variation, right? So consider this car that's being detected in this driving scene from the cityscapes data set. Naturally, if you change your viewpoint, the scale of the object and the context is going to change significantly. And similarly, while this image was taken in the day, things look really different at nighttime because of things like changes in illumination. And in this case, it's also raining in the scene. And things also look quite a bit different across geographies. So while this image was taken in Germany, if you were to consider a driving scene in India, you can see that things look quite a bit different in some more subtle ways than others. So for one, people are driving on the opposite side of the road. The scene is a lot more crowded, but also you end up seeing these kind of novel categories like a rickshaw or a lot of these scooters that you won't see too many of in Germany. And finally, things also look different based on how the data was curated, right? So on the right is an image from the Grand Theft Auto 5 game. So it's from a game simulator, and despite the impressive photorealism, you can still notice that it doesn't look quite real, and there are subtle kind of differences between how things look in simulation and reality. And so the consequence of this is that while we've made unprecedented success with deep models and all kinds of computer vision tasks, and can do really well when evaluated on held out data from the same distribution, that kind of breaks down a bit when you evaluate on out of distribution data. So consider this image on the left, and on the right, we're looking at a semantic segmentation output from a trained ResNet 50 model. And it's doing a pretty good job when you have a clean image, naturally. But if you were to even slightly corrupt your input image with JPEG compression, or were to add, say, per pixel like snow noise, you can see that the predictions degrade significantly. So maybe you might say, we just need more labels, we just need more data, and that solves all problems. So why not just do that? So there's a couple of reasons. One, quite intuitively, is because of labeling is expensive. So if you want to do label semantic segmentation scenes, I think people have done a cost analysis, and a single frame costs up to $5 for an annotator to label per pixel. If you want to do this for a task like medical diagnosis, you need really high-skilled annotators like doctors, and that can drive up costs. And if you want to do a task like 3D pose estimation, you're going to need specialized motion capture hardware. So that's also makes extensive labeling challenging. And even beyond labeling cost, I think an important challenge is that most real-world data distributions have a long tail, right? So you have, consider something like self-driving or an object detection on self-driving scenes. You're going to have some categories for which you have a lot of examples, like cars and bicycles. But you may have fewer examples for rare subtypes of cars, like a Cybertruck, or maybe a rare composition of a bicycle in the back of a Cybertruck in the desert. And you might also have entirely novel concepts, like all of these rickshaws, or my personal favorite on the bottom, like all of these people sitting on top of a bus, which is, again, from the Indian driving data set. So again, you might push back saying, aren't we in the age of foundation models? Does this even matter anymore? We have these giant models that are trained on essentially the entirety of the internet and can solve all of these tasks in conjunction. And I think that's a reasonable criticism. So maybe we can just try something like segment anything from, which was released by Meta earlier this year. and look at how it does on a few images. So the same images before, and again, it's a foundation model for image segmentation. It's been tasked with just producing a plausible image mask for every object in the scene. So naturally, for this kind of an image, it does quite well. It gets cohesive masks for all the distinct objects in the scene. But how about this nighttime image, right? Well, it doesn't do quite as well here. So it gets only partial masks for some of the cars. So this is admittedly not a straightforward example, even for a human to label. And how about this scene from the Indian driving data set? Here too, it does well on certain objects, but not so well on other things. Kind of ends up detecting some spurious masks for things that aren't really an object in itself. And so today I'm going to be talking about how for deployable computer vision, we need models that are both robust and resilient. And what I mean by that is, by robustness, I mean just the ability to generalize to adverse conditions, to generalize to things you haven't seen during training. And by resilience, I'm talking about the ability to recover from adversity, to kind of be able to bounce back when you see an unforeseen distribution shift that you can't readily generalize to. Right, so to make that more concrete, I think it's useful to kind of revisit the machine learning lifecycle. So where you have a trained domain where you collect and label data and train a model, and you deploy it in the wild in a test domain or a target domain, which is unknown a priori. So of course, you start off by annotating some data, you train a model, you validate it on some held out data, and you deploy this model. And then you kind of monitor its performance. And if you're finding that it's kind of not working in certain cases, you might need to adapt and update this model, perhaps by collecting more data, right? So it's kind of a cycle that we're all familiar with. So today I'm going to be talking about how we can make models more robust proactively by leveraging simulation to augment the long tail of real training data. I'm going to talk about how we can make models more resilient reactively by doing domain adaptation. And finally, I'm going to switch gears and talk about recent work where instead of thinking of how we train models, we look at how we can validate models better. So how can we stress test visual models for deployment by generating challenging test cases? Right. So yeah, are there any questions before I kind of dive in? Right, so just before I dive into the first project, just some general notation that I'm going to use throughout. So we're going to assume that we have an input image X sampled from a data distribution. Say for a task like semantic segmentation, we'll have a task label Y, and that sampled from a task label distribution. We have a joint distribution, and let's use S and T to denote source and target domains, and let Z be a latent variable. And all we're given is that we know that these joint distributions may shift across in your train and test domains. And we want to learn a model H parameterized by theta, which can be decomposed as a feature extractor phi and a classifier G that maps the input to the output. And our goal is to minimize the expected risk over held out target data, right? So we want to learn a model that can generalize as well as possible to held out data from the target domain. Right, so first I'm going to talk about how we can leverage simulation for building more robust models. And this was work done in collaboration with NVIDIA Research, and it's a method that we call conditional alignment and reweighting, or CARE. So in this project, we wanted to consider how we can account for the long tail of real training data. So in safety critical tasks like self-driving, it's pretty common to have access to a high fidelity simulator, right? So naturally, if you have access to such a simulator, you can simulate a really large label data set, and you get labels essentially for free. And you're going to have humans go out and label some data in the target. And so you have the setting where you have a large labeled source data set and a modest size labeled target data set. And you want to learn a model that generalizes to the target. And interestingly, although there's a lot of work in domain adaptation, there isn't really much work that looks at this setting where you have lots of labels in the source and the target. And so we wanted to kind of address this research gap and think about how to leverage the simulated data in this like label privilege setting. So as our task, we considered just 2D object detection, right? And we have a simulated source and a real target data set, and both are labeled. And we want to generalize to the target. In this case, it's the cityscape self-driving data set. And we wanted to just look at some baselines, right? So if you consider the mean average precision at an IOU threshold of 50, if you train a model only on synthetic data and test on held out target data, you get to 41.8. Naturally, if you train and test using real data, you do quite a bit better, right? You get up to 62. And if you were to just naively mix the two domains, right, using some sort of 1:1 within batch ratio, right? So you're essentially just augmenting your data set.
But are you doubling the size of your data set?
Yes.
Okay.
Yeah. So you'll see that you get a small bump, about 2.7 points. But our main question was, can we do better? And our hypothesis was that we need to necessarily bridge the sim to real gap, right? And the sim to real gap can be decomposed into sort of an appearance gap and a content gap that I'll describe on the next slide. So for appearance gap, quite intuitively, even at a pixel level, because of things like changes in sensors and so on, things look different. Even road pixels tend to look different in simulation and reality. And similarly, even at the instance level, in terms of things like reflectance of surfaces, you have disparities in how things look. And as for a content gap, you can see that in the synthetic data set, you have a lot more person annotations than you have car annotations, and that trend is kind of reversed in the real data set, right? So that's just a shift in task label distributions. And a slightly more subtle notion of content gap is in scene layout, right? So if you consider, say, the car class, and if you look at the distribution of car sizes, so over here, we're showing a heat map where it's the normalized count of car sizes expressed as by the width and the height of the ground truth box as a fraction of the size of the entire image. So that's height as a percentage of the whole image and width, right? So naturally in the simulation, in the simulated data set, you have this clean kind of distribution that only spans a particular range, but in the real data set, you have a more diffuse, more diverse distribution. So you have a lot of cars that are kind of taller than they are wide for some reason. And you can do the same thing for car location. So in simulation, you have, cars showing up in only this kind of constrained region of the image. So we're looking at a spatial heat map here. And in the real data set, it's kind of a lot more diverse. So cars show up all over the image. Right, so so as a baseline, we considered a simple two-stage detector, FOSSER or CNN, and we also have results in our paper with more recent methods like WIDDET and so on. But just for simplicity, consider this as a baseline where you have a backbone and a region proposal network and an alignment layer. You have a box predictor that's doing minimizing a classification and a bounding box regression loss. And so we propose a method that we call conditional alignment and reweighting, or CARE, where first, let's consider the reweighting. So the idea here is instead of naively optimizing these losses, we can quite naturally use the fact that we have access to labels to kind of reweight and do importance reweighting for both of these losses. Specifically, we can do two forms of reweighting. We can do class conditional reweighting, which is fairly standard. So since we care about mean average precision, which weights all classes equally, we can just do some sort of inverse frequency reweighting, right? But beyond that, beyond just doing inverse frequency reweighting, we can also do class conditional box reweighting on the source. So what that means is we can do importance reweighting to upweight the loss for source boxes that have a size x size width and denoted by the W and H, which is width and height, and a location x and y that is kind of underrepresented in the source. So like a natural importance reweighting kind of formulation, you want to just upweight these boxes for a given class. And again, using the fact that we have labels, we can actually approximate these quantities. So we can use something like kernel density estimation and fit kind of S-point estimates to for each class. We can fix like a KDE estimate to give us these values, and we can plug them in during training.
So I retained very little of that. So I get that you're reweighting things.
Mm-hmm.
You're reweighting the source data. You want to upweight data for, in this case, with this like width height
right.
of instances that have a underrepresented width and height.
Yeah.
How are you using the target data? Are you not using it?
Yeah. So so the numerator. Okay. Laser doesn't work on that. Okay, never mind. So the numerator there is the P of T. So you're trying to use the KD estimates that you've computed from the target, and you're trying to see how likely is a particular source box under the target model, right? And if it is highly likely under the target KD estimate, but not likely at all under the source estimate, we want to kind of upweight that because we want the model to do better. Because we know that in the target, it's likely to encounter more.
So should I be interpreting this as we want to upweight things in the source data that resemble the target data?
Exactly, right. Yeah, that's exactly right. Okay, so that's just how we're going to do reweighting. And similarly, for the appearance gap, we need to do this kind of conditional alignment, where again, we can make use of the fact that we have labels to only align things across domains that belong to the same class. And we can make use of only align features corresponding to the bounding box ROI features, right? So the way we do it, but there are many reasonable ways of doing this that we also experiment with, is by learning a tiny encoder from which we extract features for every class in the source and the target. And then we optimize a cross-domain cycle consistency objective. So intuitively, what that's going to do is consider the simulated image on the left and a target real image on the right. We want the model to embed in feature space similar looking instances close to one another, right? So in this particular image, these are results from the model that we learned. These two cars are deemed to be more similar in feature space than any of the other cars in the scene on the right. And similarly here, this truck is considered more similar to this based on the cycle consistency objective. And it's kind of self-supervised. You don't really need to kind of have any additional information for that. Right, so this is the entirety of the approach, which is conditional alignment and reweighting. And we show that, and without going into too many details, we can kind of interpret this quite easily as a sim-to-real translation framework in feature space. So essentially, if you consider the source objective that we optimize, we can kind of plug in just some importance reweighting and Bayes rule, and we can get this big formulation here. But the sort of the high-level takeaway here is that here we're doing like the class reweighting, we're doing class conditional box reweighting, and we're doing feature alignment here. And a lot of these terms kind of cancel out, and what you get is a class balanced version of target risk. So essentially, by plugging in these terms, we're approximately optimizing a class balanced version of target risk, which is in a sense can be considered as translating source data to target. in feature space.
Wait, you don't have to estimate the okay. How many of the terms are cancel out?
So these cancel out, and this approximately cancels out if you can assume that feature alignment is equivalent. So we're doing this alignment in feature space, not in input space. So assuming that they are kind of equivalent, that cancels out. So
ultimately, you don't need to. I mean, I have like my internal questions that how do we can estimate the probability of each kind of bounding boxes.
Right.
And there seem to be infinitely many kinds of bounding boxes.
Right. So,
and in the final equation, it seems gone, right?
Yeah, so this is because this is the term that we actually optimize. So this is not like the default loss. So in the care objective, we can show that that can be reduced to class balance target risk. But if you're asking, how do we actually estimate distributions of the bounding boxes? We do that offline. So we just do like kernel density estimation for each class using the annotations that we have. So we fit it to, like using a Gaussian kernel, we fit like KDE estimates to the measurements that we already have in the data set. Does that answer your question?
Yeah, that makes sense. But you don't use it in the final form of the equation.
Oh, we do use it. This is kind of just an interpretation. Like we do use it. We're showing, this is just saying that what we are doing makes sense because when we do that, like this is not the default loss, this is our objective. When you do that, it is equivalent to just translating data. But if you weren't doing that, then all of this doesn't kind of make sense.
Gotcha.
But aren't you using it in the denominator there? 1 over P of TC. That's the probability distribution of
Right. So that is just the class balancing aspect. I assume that he was referring more to like the box
the
distribution.
conditional. I see.
Right. Yeah, so we have results on a few different data sets with increasing photorealism in the synthetic domain, and the number of classes kind of changes across these that are shared between source and target. And once again, our baselines that we looked at before, where we have sim and real and mixing, and in each case, we're validating on held out target data. Consider, for example, the simscapes to cityscapes plot in the middle. We show that we can get significant gains. That's a relative improvement of almost 25% by plugging in our objective, and we have ablations and so on that kind of show that each part of our approach is kind of effective in bridging this gap. And in particular, we have analysis that shows that the largest gains that we get are on underrepresented classes and underrepresented box sizes and locations. Before I move on, are there any questions?
I have questions, maybe a naive questions. How can we focus on, okay, we have a simulator, but how do we know what to simulate?
Right, so this was kind of assuming that you already have a simulated data set, right, that you've generated once, and that's kind of we're thinking about how to best use this for a particular downstream task, but a natural kind of follow-up to this is that if you've not even simulated your data set, then can you kind of learn your simulation parameters that minimize this, that maximize this transfer, right? So you kind of want to, instead of doing this reweighting, you kind of want to directly simulate scene layouts that match the target. Right. So, and I think there is some work in that space that tries to pose it like as a meta learning problem where you're trying to kind of learning to simulate data that a model trained on that data will generalize well to the target, but it's like a very contrived and like complex setting. It's hard to get to work in practice, but yeah, there has been like kind of work in that space as well.
That's the nature of the problem of we have the long tail distribution, which we have no clue about. Do you think it's hard to match to simulate something that matched that distribution?
Yeah, that's a great question. Yeah, I guess you can kind of, I think there are some things that you kind of know that you have less data for, right? So in this particular case, for example, when I worked at NVIDIA on this project, they had a lot of the long tail failure cases were things like bicyclists and so on. And so you can easily do targeted improvements on those categories by doing augmentation with simulated data and plugging in our method. But there are going to be a lot of edge cases that we may not even kind of trying to catch those edge cases so that you know what to simulate is its own research question and kind of ties in really well with the last part of my talk, where I'll be talking about how can we even find what failure cases exist in your data set so that you know what to simulate. Okay, so now I'm going to be talking about some of our work on domain adaptation. And this was kind of a line of work done with collaborators at Georgia Tech that led to a few publications. Right, so we've talked so far about robustness, and now we're going to talk about kind of generalizing or rather adapting to unforeseen distribution shift. So, unfortunately, if you have a self-driving car that needs to drive in like a wildfire haze sort of thing, you don't want it to completely break down, right? You do want it to adapt to unforeseen distribution shift. And this has been studied extensively as unsupervised domain adaptation, where you assume you have a large labeled source data set and you want to adapt it to an unlabeled target data set. And there's been a lot of work in this space. There's been over 500 papers on this particular that this repo has tracked. And for instance, on this GTA 5 to Cityscapes benchmark for semantic segmentation, the absolute improvement has been pretty impressive, almost 50 points, right? But despite that, the actual adoption of unsupervised domain adaptation in say, industry has been fairly low. And we believe that this largely has to do with some unrealistic assumptions. So as a very brief primer, a lot of these unsupervised DA methods focus on distribution matching between the source and the target in a shared representation space, using something like domain adversarial learning. You're trying to learn a feature space that can successfully fool a domain classifier so that source and target features are indistinguishable. And these methods work fairly well at overcoming data distribution shift, but they implicitly assume that your task label distributions are the same or they're similar. So kind of if your source data is kind of balanced, then you're assuming that your target label distribution also needs to be somewhat balanced, despite the fact that you don't actually have labels, right? And it's been shown that these methods provably fail when that assumption is violated. And in truth, we don't actually have any control over target data, right? So a lot of real data sets have this kind of long tail distribution, and we might have this case where we want to adapt to an unknown target distribution, which might be long-tailed or it might be balanced, but since it's unlabeled, we don't actually know, right? So how do we accommodate both data and label distribution shift simultaneously? And distribution matching has been shown to fail. So instead, we looked at self-training, which has been kind of a successful paradigm in related problems like semi-supervised learning and self-supervised learning. And importantly, we were considering self-training because it doesn't make explicit label distribution assumptions. So for self-training, let's just consider a toy example, right? Where you want to distinguish between images of bears on the left and images of very bear-like dogs on the right? And let those outlines denote the ground truth manifold for these classes. And say we start off with some decision boundary, right? Shown by that dotted line. And on the left, we're predicting bear, and on the right, it's predicting dog. And so it's getting some things right, more things right than it's getting wrong. And in self-training, what you do is you would treat these predictions as pseudo labels. You would treat them as if they were real labels and retrain your model on these pseudo labels. And then you would update your decision boundary. And hopefully, while you're doing something like entropy minimization, and hopefully you'll end up in this nice case where you finally end up classifying everything perfectly, or else you kind of do that iteratively until kind of convergence. So the assumption here inherently is that you have this good initial set of pseudo labels. But in reality, in unsupervised domain adaptation, because of the train test gap, a lot of your initial pseudo labels are actually pretty bad. And you sort of more like this case where you're making more mistakes than you're getting right. And if you were to retrain, you'll end up with kind of catastrophic error accumulations. You'll end up getting everything wrong. And that kind of does happen frequently, especially on more severe domain shifts. So what if we were to only selectively self-train? So what if we had some way of identifying which of these predictions can we trust more and only use the pseudo labels for those? Then perhaps we could do better and end up in this nice case where we want to be. But then naturally the question is, how do we even identify these examples? So something simple and plausible you could do is just let's look at confidence of the model, and let's look at how far this instance is from the decision boundary and use that as a measure of reliability. But this kind of metric has been shown to be miscalibrated, unreliable under a domain shift. So instead, we focused on a different metric where we look at the predictive stability of the model under image augmentations, right? So we generate a random augmentation for an image, and we look at the model's prediction on this augmented image. And if the prediction changes or if the predictive stability is low, then we consider that as an unreliable instance. And so we're not going to trust the model's label there and vice versa. And importantly, this is kind of similar to what a lot of self-supervised learning methods, especially contrastive learning, do, but we aren't really optimizing this. We are using this as a probe to determine reliability of an instance, right? So we're trying to look at predictive stability as an indicator of reliability. And then we can just do selective entropy minimization, where we either increase model confidence if it's reliable and decrease it if it's unreliable. And this can be kind of instantiated into an algorithm that we call augmentation consistency guided self-training, where for a given unlabeled bare image, we're going to generate random augmentations. We're going to get predictions on all of these, right? And in the first case, maybe the argmax corresponds to the bear class, which is correct. In the next case, it's dog and so on. And we're just going to measure the consistency of all of these predictions via some kind of voting scheme. And we're going to use that as a measure of reliability. And if it's consistent, we're going to say, hey, this seems reliable. Let's increase the model's confidence by minimizing entropy. And otherwise, instead of throwing away unreliable instances, we can actually reduce the model's confidence by maximizing entropy. And we have some additional kind of regularizers and losses that are typically used in DA. And this is kind of the whole approach. And it's a very different paradigm from the traditional distribution matching in that we are essentially doing selective self-training, where we are incorporating instance reliability based on predictive stability. And this extends pretty readily to other tasks, like say test time adaptation for semantic segmentation, where we need to do a few tweaks to make sure that it kind of works for this new task for dense prediction. So you maybe need to kind of, you need to maintain per pixel correspondence. So the way we do that is you can get a crop and you can apply a jitter and resize it and use that as your auxiliary view. And you need to maintain per pixel confidence. So you apply the same augmentation to the prediction of the original image. And then we have these two aligned views that again, we can measure consistency across and use that to optimize a selective self-training loss. And yeah, in follow-up work, we even kind of try to modernize the DA stack and try this for self-supervised vision transformers, which are gaining a lot of traction. So things like masked autoencoders or Dino, right? And in that case, instead of using random augmentations, we find that we can actually do better by generating a proxy task that mirrors the self-supervised learning objective. So for something like masked autoencoders, we can do some notion of attention seeded masking. So we can kind of generate multiple masked versions of the same image using the attention to kind of seed that and make sure we are capturing salient regions. And we can use those as our augmented views that we measure predictive consistency under. And we kind of show that this works better than our previous scheme when you're working with a self-supervised VIT. And the main kind of finding here is that we want to design a reliability probe that mirrors the self-supervised learning objective. Right, so we have results on a bunch of standard data sets and across both task image classification, semantic segmentation, across many different architectures, initializations, and so on. We show pretty strong gains with our method on all the settings that we considered. And in terms of qualitative results, on the bottom left is prediction from an unconstrained self-training method like TENT, right? And TENT, you can see, gives you reasonable predictions, but with our kind of selective adaptation method, you can get, and also this is in a test time adaptation setting, so it's more constrained, you can get cleaner kind of boundaries and recover performance on small objects and tail categories. Are there any questions on that part? Otherwise, I'm gonna get the last part of my talk.
So for the augmentation technique that you just mentioned, is it able to predict, like improve the prediction on the target distribution, where like if you directly apply your model to the target distribution is, originally it's like you get like misclassified more than correctly classified.
Yeah.
It's able to do that?
Right, that's a great question. So yes, in many cases, and I think this is a great example of that. So what tends to happen with unconstrained adaptation is that, which is shown here in the bottom left, if your initial predictions are not great, they're not shown in this image, but typically what happens is that for difficult categories like a stop sign or a traffic signal, right? If your initial predictions are not great, and if you do self-training in an unconstrained fashion, your predictions are going to get worse over time, and you're going to have error accumulation, and you're going to completely miss out on that object. But with our kind of selective approach, where you also consider the reliability of the prediction, you can see that the traffic sign is kind of, we kind of can recover performance on that. So that's kind of one example of a case where, I guess this doesn't quite show that because we don't have a plot of what the predictions starting out were. But yeah, we do find many times that this can kind of recover from cases where you're starting out with a poor initialization.
I have a quick question about this attention-seeded masking augmentation thing. My understanding is that you use kind of like this pre-trained transformer model to then select like the most salient parts of the image and then mask away basically the ancillary parts of the image.
Right.
So that like presumably you would be more robust under distribution shift. When you do this under the target data set, like are you concerned at all about domain shift of like the VIT model? Like for instance, this attention mask might not be like reasonable under a target distribution that it's like far away enough from
that's a great
source.
That's a great question.
But you don't find that empirically that it's a problem?
Yeah, we don't find that too much empirically, and I think there's also sort of work finding that just kind of self-supervised learning methods like Dino learn really interpretable attention maps in an unsupervised fashion. So kind of, it seems like they pick up on objectness and things like that, and perhaps those generalize better across scenes. But yeah, I guess it is worth exploring that, whether there are cases where like the attention itself is unreliable, and maybe we just want to do, we also have like a random masking scheme, so you can still do random masking, but yeah, that's a great question. We haven't really studied that.
Okay, nice.
Okay, so finally, I'm going to be talking about some recent work where we're considering how do we validate models better. Okay, so this is called LANS, which stands for Language Guided Counterfactual Images. And this was again work done with collaborators at GT. So what we're really interested in here is not in training better models, but in finding what the failure modes of a given model are before we deploy it. And the traditional paradigm for this has been, collecting a large data set like ImageNet and tracking performance on its test set over time. And if that's going up, then we kind of call it a day and say that, our models are getting better. But there are some fundamental limitations with this kind of approach. So for one, the test set is IID, right? So it's independent and identically distributed to the training set. So it's also going to be long-tailed like the training set. And so you're not actually going to capture the long tail because you're going to have a long tail within your test set. Next, these test sets are static, right? You have a fixed ImageNet test set that doesn't change across different models or even across time. And this is a problem because different models can have different failure modes, right? Not all models will have the same vulnerabilities. And finally, typically people just look at aggregate metrics, something like top one accuracy, which treats all failures interchangeably, but in practice, there are some failures that are a lot more egregious than others that we kind of need to flag. So we find that this can kind of lead to a false sense of security. So consider sort of this image from ImageNet, which has been annotated as dog sled, right? And the caption for this image is huskies pulling a dog sled. And if you look at the predictions from a ResNet 50 model, you'll see that it assigns 53% confidence to dog sled, which is the ground truth class. And then it also tries to predict the breed of the dog. And performance on this class as a whole is also quite high. But if you were to now, replace the husky with like a Labradoodle, right? You'll see that it no longer predicts dog sled, and it tries to guess the breed of the dog, which in itself is not a problem. But what's interesting here is that it seems to be, in neither of these cases can you see a dog sled in the picture, but it seems to be associating the presence of a husky with there being a dog sled. And this holds for other breeds, right? If you were to change this to a Pomeranian while keeping the rest of the scene unchanged, again, you no longer predict dog sled in the top few predictions. And you may say that, hey, these Pomeranians are not even sled dog breeds, so that's totally fine. Like, why would you want it to predict? So we can try, other breeds of other sled dog breeds, like a Malamute, for instance. But even then, the prediction confidence goes down quite a bit. And if you change it to a Samoyed, which is also a sled dog breed, again, it tries to predict the breed, no longer tries to predict dog sled.
So why is this bad behavior? It's not correct.
Right, exactly. So it's not, I guess, whether or not it's bad behavior, like the value judgment kind of depends on how you plan to use it.
Sure.
Right. So what all this is saying is that all dog sled images in ImageNet are huskies, are like huskies pulling. So if you want to deploy this in a different country, that's not gonna work well. So so we aren't really saying this is a problem or like
But
this
it just
particular.
doesn't agree with the label.
Yeah, we're just trying to say that there is this sensitivity to the dog breed. Whether or not it's a problem is something kind of the practitioner has to judge. And our goal in this is to kind of surface these kinds of reliances, right? Not really kind of assign a good or bad label to them. And this is not entirely dissimilar from what we do for software testing, right? Where we write unit tests and try and see whether models can pass all these kinds of tests. but we don't typically do that same sort of thing for machine learning models. So in this project, we wanted to kind of design dynamic test suites. So what that means is, given a trained model and some IID test set, we want to have this test image generator that can give you an augmented test set of challenging examples and a sensitivity analysis of what this particular model is most sensitive to for a given class. So maybe its performance changes a lot as you change the leaf color, or if you change the weather in the scene, right? And essentially what we're wanting to ask are what if sort of questions. So what if the leaves were orange, or what if the weather was snowy, right? So hypothesize different conditions that aren't in the test set. And sort of a natural thing to do in this case, perhaps, is to leverage all the progress we have in generative modeling recently. So essentially, so what if kind of questions lend themselves very naturally to kind of counterfactuals and like causal interventions. So what we want to do is we want to ask what is the confidence that the model still thinks this is the howler monkey if the color of the leaves around it would change from green to orange, right? So this is like a standard counterfactual query where we're actually intervening on the value of an attribute. And maybe there are different reasonable ways to generate these counterfactuals. So maybe we can do it directly by intervening on pixels, right? So we can use something like StyleGAN and have this kind of interpretable latent space that you can traverse to kind of change different attributes. You can want to change the color or the grass and so on. But this is kind of challenging because you need to learn this disentangled space. You need to discover these directions, and you kind of need to actually traverse them, which is hard to do for very open-ended and general kind of queries. So instead, we propose just intervening on language, right? So consider this same image. If I were to tell you, give you that caption, a black monkey sitting on top of a tree with orange leaves, and show you this initial image, most of us would end up sort of imagining an image like the one on the right, right? So language is kind of neat for this because it's a more amenable scaffold to do intervention. It's discrete, and you can kind of capture salient concepts and abstract away kind of irrelevant details. So that's exactly what we try to do. We try to do language-guided counterfactual image generation. So given this test set and trained model, we first generate a caption, like a black monkey sitting on top of a tree with green leaves. We perturb this caption, and I'll talk about how shortly, to change only one particular aspect of this caption, but we do not allow edits to any word that is similar to the ground truth. So we don't want to mutate the ground truth. Yeah, so we kind of ensure that. And now we want to generate an image that's conditioned on this new caption and the original image, which we kind of can do DDIM inversion for. We're using a latent diffusion model for image generation here. And then we can use some targeted editing technique to generate the image on the right. And we can look at the model's prediction on this image, in this case, gorilla with 75% confidence. And we can measure how sensitive is the model to this particular intervention. So how much does its confidence in the ground truth, in this containing a howler monkey, change if you were to change only the color of the images and change nothing else? Does that make sense? Right, so for captioning, we can use any off-the-shelf captioning model. We use BLIT2. And for caption perturbation, we fine-tune a large language model, specifically Llama. So we collected a really small data set programmatically using ChatGPT, and we use that to instruction fine-tune a Llama model with low-rank approximation fine-tuning, given to follow prompts of this sort. So generate all possible variations by changing only the dash of this given sentence, and yeah, like with Llama 2 now, we can kind of even skip this step, since we find that we can even just do zero-shot prompting. We don't need to train it. But getting back to what we trained the model to do, we can now make edits of a specific type. So we can say, change only, say, the adjective in the sentence. And if there is no adjective, then add one. So it'll change like a hockey puck to a large hockey puck and so on. Right? So you can get these kinds of structured edits. And we can generate a large data set of 35K perturbations doing this. Right. And finally, for the targeted editing, we use a latent diffusion model with prompt-to-prompt editing. And as a really brief primer on this, we use this technique called prompt-to-prompt editing. So to do prompt-to-prompt editing on real images, you first need to invert images to latent space. The way this paper called null text inversion does it is you do an initial DDIM inversion, and you use that initial trajectory as a pivot, and then you minimize the mean square error between that initial trajectory, and you optimize only the null text token embedding. I mean, it's not really important to like kind of understand all of that, but it's just a way to map this image to a good latent space representation from which you can accurately reconstruct the original image. So now that we have this latent space inversion Z at a particular time step, we can get some big pixel features corresponding to that can be decomposed as a query and a key. And then the stable diffusion model has cross-attention layers that kind of maps these to cross-attention maps. So there's a unique cross-attention map corresponding to every token in the prompt. So that captures kind of the interaction between language and vision. And this paper shows that you can now do targeted insertion of these prompts during these attention maps into the cross-attention maps for your new prompt. You just kind of need to do targeted insertion during the diffusion process, and that's the way in which they can do targeted editing. So you can get an image that satisfies your new prompt and your original image. And so here are just some examples. So, with this, we can do subject edits and change like husky dogs to schnauzers. And we can make background edits by, say, adding snow and say like a photo of a young boy hanging from a metal bar on a playground, and we can make the playground snowy. And we can go from a photo of a howler monkey to, say, a sculpture of a howler monkey. And so the first thing we wanted to do is to ensure that we are generating, while the images that we generate look good, we also need to our goal is to stress test models. So we need to make sure that the test sets are actually challenging. So the way we do that is we look at what is the accuracy of off-the-shelf pre-trained models like a ResNet 50 or a vision transformer or ConNext when evaluated on test sets generated by our method. So as a reference, this is the performance of the original on the original ImageNet test set for a subset of its classes that are included in this benchmark called Hard ImageNet. And just as a control, we look at performance on reconstructions of this image, of the original image from stable diffusion without changing the prompt. I'm going to skip this baseline. We designed like a random baseline for our method, but importantly, we find that with our method, which is Lance, the yellow bars, we can get bigger drops in accuracy, which kind of is showing you that these are more challenging to models, while still we also have ways to evaluate like the quality, like the FID scores and so on, to make sure that those images are still realistic. And we can kind of do analysis by different kinds of perturbations. So for example, we find here that all models are most sensitive to background edits because they rely a lot on spurious cues. And specifically, models like ResNet 50 and CLIP are a lot less robust than more recent models like VITs and ConNexts. But kind of the natural follow-up is how do we actually derive any kind of actionable insight from this? Because this is all still like at a single image level. So we have a fairly simple method that we find to work quite well, where we just first embed. So let's C of X be the caption or the prompt for a given image, and X dash is the generated counterfactual. So we just embed the captions for both of those images. We run some kind of clustering on those, on the distance and embedding space. And then we visualize the different clusters ranked by their average sensitivity. So we try to find consistent edits that lead to a large variation in model performance. And that's maybe better understood like by an example. So for example, one of the top for a given class, like for Howler Monkey, the top ranked, the highest average sensitivity is for a perturbation to leaf color. So it's a 40% perturbation over a subset of images, where, for example, we find that these are the starting images. And if you were to go from leaves to orange leaves, and you'll see that the model doesn't really do a very good job here. It actually adds something that looks like an orange fruit, but the model's kind of confidence that this is a Howler Monkey goes down by quite a bit. And similarly, in this case, if you go from a green field to a pink field, there's quite a lot of fluctuation in the model's confidence. And similar, but there are cases where it's a little more robust. So if you go from green field to snow-covered leaves, performance only, the confidence only goes down by a little bit. But I mean, these are just some representative examples, but on average, the model is quite sensitive to the color of the surrounding foliage for this given class. And you can also find other kinds of more, you can kind of rediscover like well-known failure modes like domain shift, right? So even for the sunglasses class, if you were to change from photo to painting, model performance consistently drops. And it isn't very good at recognizing sunglasses, even for like fairly subtle changes. So you're just rendering just a rendition of this original image as a painting. And in terms of like next steps and where we want to go with this next is, so we can kind of go beyond like image classification to tasks like detection, where it's more complicated because you have interactions between different objects, and we can do scene level interventional discovery. For example, find that, if there's like a Coca-Cola truck behind this police vehicle, then it can no longer detect it. Something that we've been trying to do quite naturally is we can actually use the sensitivity as a reward and do like RL from not human, but RL from model feedback, and kind of discover the failure modes for a given model, right? So try and do dynamic test sets. So for every model, have a different test set that is meant to challenge that model. And something that, we think could be interesting is kind of this whole line of like visual programming, where like Viper GPT and VisProg, where you're trying to generate, and this is kind of more useful for open-ended compositional queries. So you want to find out if the model fails in more complex compositions and so on. So you can kind of do that by generating code, like expressing a query as code and having it compile that. And we're working on releasing this as an open source robustness toolkit, where we want to be able to just pip install it and use it to, given a model and a data loader, try and surface all these kinds of error modes and generate plots. And yeah, so besides what I talked about today, I've also worked on other problems in the robustness space, specifically in active learning for transfer, trying to do geographical domain adaptation, where we're concerned with how do we adapt models trained on, say, images from North America to generalize to images in Asia. And also a more general framing of the dataset bias problem, of course, has many fairness applications. So try and discover spurious correlations and mitigate reliance on them. And also trying to do extensive benchmarking of all the kinds of off-the-shelf models that are available today to see how robust they are relative to one another. So this is just some of the work I presented today, and yeah, some of my other work. I'm happy to talk about it offline if anyone's interested. And yeah, to summarize, today I talked about building reliable computer vision systems by leveraging simulation for robustness, by doing domain adaptation for resilience, and by generating counterfactuals for stress testing. And yeah, I'd like to thank all my collaborators at Georgia Tech and the Hoffman AI Lab. And yeah, that's my presentation. Thank you.
So I have a question about the stress testing. So if you use the generated image that you currently use to stress test as part of the training data, will that lead to the performance on your original test set to increase or to decrease?
So actually, I think that's a better question for Lisa, because I think that's exactly kind of what her paper does.
What was the question again? Sorry.
Like if you use the generated images as part of the training data,
It increases.
increases?
Yes.
Okay.